Hi, my name is William Bushy, and this is Lab 5 for Georgia Tech Physics 2. So the introduction to this lab is to help understand Faraday's law and magnetic braking, which is when a magnet within a closed tube, as it's falling, it will create an induced magnetic field that will oppose the motion of the magnet, meaning that a magnetic force will be acting opposite the force of gravity, so in theory it should affect the motion of a magnet falling in the closed tube. So key equations for this are the magnetic field equals mu naught over 4 pi times 1 over r to the third times 3 mu r hat squared minus mu. The force on the loop is the current times 2 pi r times the magnetic field times the cross product of mu times the magnetic field. And delta phi over delta t, where phi is flux in this case, is 3/2 mu naught mu v r squared y divided by r squared plus y squared to the 5/2, which is equal to EMF or voltage. So the force of gravity in this case is the mass of the magnet, didn't know how to do mu, times gravity times j, which is the direction of travel. And the final velocity is the initial velocity of the magnet plus the net force divided by mass, which is acceleration times time. And current in this is EMF divided by resistance. And resistance final is the final radius is the initial radius plus the average velocity times delta t. So constants that were used in this setup: the tube length was 0.3 meters, the aluminum foil thickness was 0.005 meters, the inner radius of the tube was 0.021 meters, the outer radius was 0.026 meters because you account for the aluminum foil thickness. The magnet's mass was 0.023 kilograms, mu was 3.206, the average time, that was incorrect. Checkpoint questions. A ferrous steel pipe could not be used because it would have an induced magnetic field that would interfere with the descent of the magnet. The magnet falls much slower through the tube than free space. Coding, so the width of the aluminum foil, 0.005 meters, the inner radius 0.021, and this is where you add those together. So here is the numerator, the 3 mu naught over 4 pi times 4 times pi times the magnitude of bar mu times speed times distance time the radius of the ring squared. Here is where you plug in your previous equations for the velocity and position, or radius in this case. So here was the velocity over time after 5 trials, and the time for this was 0.223 seconds, whereas the average was 0.23, and that was largely due to human error, as stated above. And from this, we found that red coloring on the computational tube was counterclockwise current, blue was clockwise, and if the magnet were flipped, because in the last case, it was blue at the base, if the magnet were flipped, it would be red at the base because the current would be going in the opposite direction. The computational model was faster and didn't account for factors like human error, and the acceleration was constant as the magnetic and gravitational forces opposed one another, and the net force was downward. That meant a constantly increasing velocity. If resistivity were reduced to as close to 0 as possible, the braking force would increase and be equal to the gravitational force, as the current would have to be much, much higher, so that would cause the magnet to not fall at all. Then cutting holes in the tube would reduce the current and make it less regular, so the braking force would be reduced and the magnet would fall faster.